all of them who are listening my PPT. First of all, my name is Bhavat Parmal. I am going to present a PPT of magnetically coupled circuit. Let's go through it. The subtopic involved in the magnetically coupled circuit is self and mutual inductance, coupling coefficient, dot determination. The objective of the topic is to understand the basic concept of self-inductance and mutual inductance, to understand the concept of coupling coefficient and dot determination in circuit analysis. Self and mutual inductance. When two loops with or without connected between them affect each other through the magnetic field generated by one of them, it is called magnetically coupled. Example, transformer. An electrical device designed on the basic of the concept of magnetic coupling used a magnetically coupled coils to transfer the energy from one circuit to another. Self-inductance. It called self-inductance because it relates the voltage induced in a coil by a time varying current in the same coil. Consider a single inductor with number of turns n. When a current I flows through the coil, a magnetic flux is produced around it, which induced a magnetic induction. Mutual inductance. When two inductors or coils are in close or proximity to each other, the magnetic flux caused by current in one coil links with the other coil, therefore producing the induced voltage. Mutual inductance is the ability of one inductor to induce a voltage across a neighboring inductor. Coupling coefficient. It is measured of magnetic coupling between two coils. The range of the coupling coefficient is 0 to 1. If it is 0, it is not coupled. If it is 1, it is perfectly coupled. But in practical cases, it will not be 1. It may be less than 0.5 or greater than 0.5. If it is less than 0.5, it is loosely coupled, and greater than 0.5, it is tightly coupled. The coupling factors depends on the closeness of the two coils, their core, their orientation, and their winding. And the formula is given below. Just see it. Dot determination. It is the main strategy to solve the circuit of magnetically coupled. Required to determine the polarity of mutually induced voltage. A dot is placed in the circuit at one end of each of the magnetically coupled coils to indicate the direction of the magnetic flux. If current enters the dotted terminal of the coil, the flux produces upwards. If it leaves, the flux produces downwards. Dot convention states as if a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is positive at the dotted terminal of the second coil. Conversely, dot convention may also be stated that if the current leaves the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is negative at the dotted terminal of the second coil. The following dot rule may be used. When the assumed current both enters or leaves a pair of coupled coils by the dotted terminal, the sign on the L will be negative. If one current turns by a dotted terminal while the other leaves by a dotted terminal, the sign on the M negative terms will be positive to the sign on the L. Once the polarity of the mutual voltage is already known, the circuit can be analyzed using the mesh method. The following example circuits are given below. The application of dot convention in the example 1. Let's see. When the current enters the coil, in both the coil, the mutual inductance is positive. If the current enters in one coil and the neighboring coil it leaves, the mutual inductance is negative. For example 1, the sign of the mutual voltage V2 is determined by the reference polarity for V2 and the direction of I1. Since the I1 enters the dotted terminal of coil 1 and V2 is positive at the dotted terminal of coil 2, the mutual voltage is M di divided by dt. Example 2, the current I1 enters the dotted terminal of the coil 1 and V2 is negative at the dotted terminal of the coil 2. The mutual voltage is minus M di 1 divided by dt. Same reasoning applies to the coil in the example 3 and 4. The 3 and 4, if discussed above, the current enter to the dot in one coil and leaves the dot in other coil, the mutual inductance may be negative. The mutual inductance is negative. If in both coil it enters or leaves in same, the mutual inductance is positive. Okay, let me see some series combinations of the inductors. If the current enters the coil, the mutual inductance is positive. So the both coil the current enters, the mutual inductance is positive, so plus 2M in the equivalent inductance. If one coil the current enters and another coil the current leaves, the mutual inductance is negative, so minus 2M. Okay, let me see some example circuits. First of all, we need to remember 2 points. The mutual inductance created in a coil is by nearing coil and induced by a nearing coil current. And if the current enters in both coil or leaves in both coil, it is positive. The mutual inductance is assumed as positive. If the current enters in one coil and leaves in another coil, the mutual inductance is negative. Okay, consider a loop. Let me apply the KVL. Normally the R1 plus R2 plus JA I1. But in inductor the mutual inductance is created due to JB and JB current, that is I2. In that circuit, the I1 current enters the coil and I2 currents leave the coil. So the mutual inductance is negative. So M I2. On applying the KVL in second loop, normally minus R2 I1 plus R2 plus R3 plus JB I2. In mutual inductance created by JB is due to I1 current passing through JA. In that JA, the current enters, I1 current enters, and JB the current leaves. So the mutual inductance is negative. Let me see further examples and more examples to clarify all your doubts and perfect clarification. Let me see the circuit. We are applying a KVL in first loop. Normally the R1 plus JA plus JB I1 minus JB I2. The mutual inductance created in JA is due to the current passing through JB. What is the net current passing through JB? Is I1 minus I2. So M I1 minus I2 is the voltage induced in JA. If it is positive or negative, we must check that place. The I1 current enters in both the coil, so it is positive. For JB, I1 current enters in JA, create a mutual inductance. So I1 current Mi1 and both are entering currents, so it is positive. On applying KVL in second loop, there is only one inductor, but the mutual inductance is created by JA by I1 current. Then in seeing that I2 current, I2 is leaving and I1 is entering the inductors, so it should be negative. I think you may understand. We move to the next third circuit. Okay, let me apply a KVL in first loop. Normally R1 plus JA I1 and minus JA I2. Then mutual inductance is created by JB. Both sides the current enters. So the mutual inductance is positive and created by I2 current. So MI2. And applying the KVL in second loop, normally minus JAI1 plus R2 plus RJA plus JBI2. Then mutual inductance created in JA is due to JB and I2 current. And seeing the I2 net current passing through JA is I2 minus I1. It is leaving from the dot and I2 is entering the dot in JB. So it should be negative. The mutual inductance is negative. On referring in the mutual inductance in JB, the net current is I2 minus I1 and I2 leaves the dot and I2 of JB enters the dot. So it should be negative. Okay, let's move to the circuit 4. Okay, we apply KVL in loop 1. Normally R1 plus R2 minus JC I1 and minus R2 I2. No mutual inductance is created due to no inductors. In applying the KVL in second loop, they two are series cases. One side the current enters and another side the current leaves. So minus 2M I2. Just assume that referring the individual inductors, I discussed about that in series combination, if the both current enters plus 2M and one current enters and one current leaves, just put minus 2M. Don't simply get some idea. For idea, just see the inductor JA. The mutual inductance is created by JB due to I2 current. In that, I2 enters the JA and leaves the JB. So the mutual inductance should be negative. So MI2 due to JB current. Then referring the JB, JA create a mutual inductance. I2 enters a JA and I2 leaves the JB. Then again minus MI2. So MI minus MI2 join minus 2 MI2. I think you may understand. Let me explain the next circuit. This is the more little tricky knot, like a more interesting case. If the three inductors are there, so the mutual inductance created in one inductor is due to two inductors. So we need to check two conditions for a mutual inductance in a one inductor. Just we apply a KVL in first loop. Normally we will write R1 plus JA plus JC I1 plus R2, then minus R2 plus JC I2. Okay, refer JA. The mutual inductance is created from JC and JB. JB create M3 mutual inductance due to I2 current. In I2 current leaves the JB and I1 current enter the JA. So it should be negative, then M3 I2 is negative. Okay, then the mutual inductance, first of all we have discussed about the mutual inductance in JA due to JB, then JA due to JC. JC the net current flows I1 minus I2. Net current flows I1 minus I2. Then M1. I1 enters the JA but leaves the JB. So again negative comes. Mutual inductance is negative. Okay. Let us assume that JC has two factors. Yeah, one mutual inductance come from JA and another mutual inductance come from JB. From JA M1 and JB M2. Okay. For JA, I1 current enters and JC I1 current leaves. So M1 minus M1 I1. Okay. For second loop, for second inductor JB, I1 current leaves the JC and I2 current leaves the JB, so it should be additive. So M2 I2 additive, okay, plus M2 I2. I think you may understand. I will repeat again. The first loop consists two inductors. So JA has a mutual inductance of JC and JB. JA has a mutual inductance of JC and JB. JA. M1 is a mutual inductance created by JC. If the current enters JA and leaves JC, so minus M1, and net current to JC is M1 minus I1 minus I2. Okay. Then JB. In that I1 enters and I2 leaves, so minus again M3 I2. Assuming JC, I1 enters JA and leaves JB, JC leaves JC, so minus M1 I1. You may understand, I think so. Let me see the second loop. Second loop that has two inductors JC and JB. Normally we can write minus R2 plus JC I1 plus R2 plus JC plus JB minus JD I2 plus, just now refer JA. JC. JA creates a mutual inductance to JC. The I1 current enters JA, but in this JC we must refer I2. I2 is a reference current. So same as I2 in the net result, net is I2 minus I1 enters. So in this the mutual inductance is positive. M1 I1 is positive. Then going to the JB. JB I2 current leaves and JC I2 current enters. So M minus M2 I2. Okay, referring the JB. I1 current enters to JA and I2 current leaves the JB. So minus M3 I1. And referring JC, net current I2 minus I1 is entering and I2 current is leaving, again minus M2 I2 minus I1. I hope you may understand what I have discussed above. Thank you for your patient hearing.